Voice ठीक है ना? Hello everyone. I hope you guys are having an amazing time over there. So today we are going to continue our discussion for AIATS Plus Phase 2, right? Mock Test 9, which was conducted on your 16th of March. I am Sri Kumaran, your physics faculty at Aakash. So let's begin. Right? So these are some of the topics which we are going to be discussing today, some of which we have already had some in-depth discussions, if you remember, right? For these past many weeks, we have been having such discussions on all these topics, right? So let's begin with our first topic of 11th class, work, energy and power. And there are some good problems as well, right? So let's revise some concepts, right? So we had discussed that a work done by a simple force which is acting on an object, and let's say it is undergoing a displacement r vector, okay? And force, as you know, is a vector, right? It has a magnitude and a direction. So we are basically revising that formula. So force as well as displacement, they are both vectors, all right? So let's say work done by force F vector, right? And let's say this force is a constant force, all right? Which means at each and every point of that displacement, the force's magnitude and direction remains the same, all right? And let's say displacement is r vector, okay? So in that case, what will be this work done, right? So what will this work done be equal to? This work done will be simply the dot product of the two, right? F vector dot r vector, which becomes Fr cos theta, where theta is the angle between both vectors, F and R, okay? Then let's say the force is varying with each displacement, right? So let's say it is undergoing a displacement r vector, but with each infinitesimal step, the force is varying. So in that case, how can we find the work done? In that case, we can write work done as not directly F into R, right? Because force is different at each value of R. So in that situation, we will use this formula. We will integrate after finding a small work done, right? That small work done would be nothing but F into dr, okay? So F dot dr vector, and here also the same thing, F dr cos theta. So let's say, for example, the angle between the two is 0 degree, right? So in that case, cos 0 will become 1. So it will become simply F dr integration. Or, so let's say the force is always perpendicular to that each small infinitesimal displacement dr. So if it is perpendicular, that means theta is 90 degree. So it will become F dr cos 90, which is 0. So this means dw is 0, that means w will become 0 in that case. But this formula we can use, okay? And then we had also discussed, right, that work done by all forces is equal to change in kinetic energy, right? So kinetic energy, I am denoting it by the symbol K. So change in kinetic energy, which means final kinetic energy minus initial. And what's the formula for kinetic energy? Half m v square, okay? So half m v final square minus half m v initial square. So if you want, I can write down v final square minus half m v initial square. Remember, this is work done by all the forces that are acting on the block, okay? But let's say only one force is acting, this F is acting. In that case also, work done will be the same formula. You can use it, all right? So let's see what the first question is talking about here, right? It's a very straightforward question, this one, and this came in your previously concluded AIATS, question number 10, and it goes as, a particle is moving along a straight line from point A to point B, the position vectors for points A and B are given. Okay, so that means, right, so this is for point A, all right, so this is for point A and this one is for point B. Okay, and continue reading the question. Then what are they saying? If force is given, is acting on the particle, then find the work done by this force. This is what you have to find out. So first, before we begin, please note that this force, is it constant or variable? It is constant, isn't it? See the components of I, J and K, it's all constant values, and as a whole as well, this vector, this force vector will have a particular direction. Okay, so for example, if this force is along this direction, it will continue to be in that direction itself. Okay, the magnitude and the direction will remain the same. That is why we can say this is a constant force. All right, and we have been asked to find the work done. So let's use the formula that we just now wrote, right, a few moments ago. So which formula we will use? The formula for constant force, right? F dot R vector, isn't it? You see here, if you want, I can also write down, okay, just for you guys, this is for constant force and this is for variable force. Okay, so if you want, I can write down here. That way you can remember also constant force, and this one is for variable force. So this F dot R we have to do, right? F vector is already given, but R vector, how will we find R vector? R vector, what is it? R vector is your displacement vector, isn't it? Displacement vector, right? And how will we find the displacement? Final position minus initial position, right? Final and initial are given, right? It is going from A to B. So how will we find this out? It will be nothing but final is B minus initial is A. All right, this we have to use. So just subtract them, B minus A. Just do B minus A, see here, 5i minus 2i. What will it become? 3i. So it will become 3i cap, then minus 3j minus 7j. So that becomes minus 10j cap. Okay, and then B minus A, right? So minus 6 plus 3. Why I did not do minus 3? Because it is B minus A. So this minus minus will become plus. So minus 6 plus 3. So that becomes minus 3 k cap, right? And write the unit as well for this displacement vector, which is meter, right? So force vector is given, R vector you have found out. All we have to do is find the work done. So first write the formula for work done, which is simply F dot R, right? And what are the rules for dot product? This, if you remember, we had discussed. Yeah, good afternoon, Dashrath. So if you have to take the dot product, what you have to do, just focus on the like components. Okay, so I cap with I cap. So it will become 20 into 3, right? F dot R, so 20 into 3 is how much? 60, right? Why not, I'm not taking 20 into 10? Because here I cap and here is j cap, right? So I cap dot j cap is how much? I cap dot j cap will become 0. Why? Because what is dot product, by the way? Fr cos theta. That's what we wrote, right? So it will be mod A mod B cos theta. So mod of I cap, magnitude is 1. Magnitude of j cap is 1 into cos of angle between them. What is the angle between I cap and j cap? Remember, I cap is along x axis, j cap is along y axis, right? So what is the angle between them? 90 degree. So it will become cos 90. So that's why 0. So remember, in dot product you can directly do I cap with I cap. All right. So minus 30 into minus 10 will become 300. Then 15 into minus 3 is minus 45. Fair enough and simple enough. So just add them up. 360 minus 45 will become how much? 360 minus 45 will become 315 joule, right? So which means option number 2, right? So I hope everyone has got this one. We did some small revision for this topic, right? Now let's do some revision for the fourth formula which I had written over there. right, for kinetic energy, right? So if you see over here, it's pretty much the same question, just I have tweaked little things, such as I've added the mass of the body, which is 2 kg. Okay, so that means m is equal to 2 kg. The rest, everything remains the same. The particle is, or the body is going from A to B, so displacement vector will remain the same. And if you see the force vector, that is also same, isn't it? 20, 30, 15, just what we did. So that means the work done will also remain the same. So we can directly use our result from the previous question. So what was our work done coming as? 315 joule, right? Let's continue. And they are saying this force is acting on the body, which we already know, and its speed at point A is given. So initial speed is given, isn't it? So let's say, for example, the particle is going from A to B, all right? A to B, and speed at A is given, and they're asking then its speed at point B is. So initial speed is given, final speed they're asking, all right? So Vi is given 3 meter per second, and Vf we have to find out. Which formula we will use? Change in kinetic energy equals work done, right? So just write that formula. So half m V final square minus half m V initial square, isn't it? M is how much? 2 kg, right? So I will do half into 2 into V final square minus half into 2 into V initial square. All right. So I hope everyone is okay with this one. So 315 is equal to, all right, so what does it become? 315 is equal to V final square minus 2 cancel, V initial is 3, and 3 square will become 9. Take this to the side. So that means V final square would become 324, right? 315 plus 9, and what is this one? 324 is a perfect square of which number? 18, right? So that means we can finally say that V final we know, right? How much? 18 meter per second. So here obviously they're asking speed, right? Because velocity, remember, while mentioning, you have to specify the direction as well. But the initial direction is not given, so we don't care about it. But the final speed we have found out. Okay, so answer is 18. All right. So let's move on. Let's move on. And this also we have done, right? We had, if you remember, talked about spring forces, spring energy, right? This pertains to the same topic. If you see, two springs, S1 and S2, have spring constants 200 and 400, right? So S1 and S2, that means, let's say the spring constants are K1 and K2, respectively. For same energy stored in the springs, okay, their corresponding spring force is in ratio. Okay, the corresponding spring force we have to find out. So same energy, right? So same energy meaning U1 is equal to U2, right? And what is spring force, by the way? Spring force is, let's say, F, and energy, I'm specifying it as U, right? So same energy, so you can write down, so this becomes half K or K1 x1 square is equal to half K2 x2 square, right? The spring energy or the energy stored in the spring, half Kx square, I'm using that formula, which is the elastic potential energy. This also we had talked about, right? So here K1 and K2 are given, all right? So you can find, let's say, x1 by x2, isn't it? So if you see over here, K1 by K2 becomes x2 by x1 whole square. Okay. So what does this become? K1 by K2 is how much? 200 by 400. That is 200 by 400 is 1 by 2. Right. So 1 by 2 is equal to x2 by x1 whole square. Now take square root both sides. So this 1 by 2 will become 1 by root 2. Okay. So I'm directly writing x2 by x1 is 1 by root 2. Right. But now they're asking the ratio for the spring force, isn't it? So spring force, so let's say F1 by F2. So what is spring force? Kx with appropriate direction, right? So for example, let's say I'm stretching the spring force will try to make the spring come back to its mean position, all right? But here we are only concerned about the magnitude. So F1 will be Kx, right? So K1 x1 upon K2 x2, okay? K1 x1 upon K2 x2. So if you can just substitute the values, you'll get the answer, all right? All right, very well. This is also a similar question, all right? Yeah, I think, yeah, this is the question that we did just now, all right? If you want, we can continue, right, which is, what was x1 by x2 we got over there? Let's continue, all right? So x2 by x1 we got as 1 by root 2, okay? So let me write over here, is 1 by root 2. Either way, the spring constants are given over here, isn't it? K1 and K2 is given, right? So spring force, we have to find their ratio, right? So K1, right? So K1 by K2, right? So 200 by 400. Let me write the values as well, all right? 200 by 400 into x1 by x2, right? Because remember, x2 by x1 we have found out. x1 by x2 will be what? Root 2 by 1, isn't it? So x1 by x2 I'm directly writing root 2 by 1, all right? So this becomes 1 by 2 into root 2 by 1. So just cancel 2 with root 2. So you remain with 1 by root 2, all right? So that becomes your answer, all right? That becomes, you can ignore the previous slide, okay? You can take this as your main question. So the answer to this one becomes 1 by root 2. Either way, I could have asked a different question as well, isn't it? So for example, here it is given same energy stored in the springs, but the question that came in your exam, that was for same spring force, what will be the ratio of energy stored in the springs? That could have been the other question. Either way, all right, so let's move on to our next topic, gravitation. We had discussed so many questions on the gravitational force, right? So here today, we're going to be talking about escape velocity of an object. So let's say it is lying on the surface of Earth. So what are the energies it has? Only potential energy. Why not kinetic energy? Because as I said, it is lying. It is stationary, all right? But what happens, right? So let's say this is mass m of that object, and this is mass capital M of Earth, and radius capital R of Earth, all right? So what is the potential energy of associated here, right? So let's call it initial potential energy, denoting it by symbol U. So what would it become? Minus GMM over R, all right? Why R? Because remember, this mass, we can take it almost outside the surface, isn't it? It's not inside the Earth, it is outside. So that means you can take this whole Earth concentrated at its center, right? And what is the separation between this small mass m and this Earth? If it were to be concentrated at its center, it would become capital R, all right? So minus G m1 m2 by distance between them, capital R, okay? Now what is initial kinetic energy? So let's say it is just lying. That means kinetic energy is 0, right? So that means this body is not going to escape from the surface. But if you want the body to escape, you have to give it some speed, okay? So let's say we are giving the speed VE, okay? This is a famous notation, all right? It has a constant value as well. We'll find out what the value is, okay? So let's say initial speed VE is given. It has a speed VE. So what will be its kinetic energy? Half mv square, okay? And remember, this is the minimum velocity which this body has to escape from the Earth, to escape the field of the Earth, all right? So what will be the total energy here, right? So total energy will become how much? Kinetic energy plus potential energy, right? So potential energy is negative. So let me directly write down minus Gmm over R. Okay, and I just now said it is the minimum speed. Minimum speed meaning minimum energy to escape. That means if it escapes with this speed, what would be its total energy after it escapes? Total energy will become 0. Why? Because it has escaped to interstellar distance. Okay, so infinity distance. So over there, speed is already 0. It is very far away. So this potential energy term will also become 0. Isn't it? It will become very large. So total energy initially will be equal to total energy finally, which is 0. Alright? Because this is the minimum speed. So what would this be equal to? Take this to that side, right? So half m VE square. So today we have derived the formula also. Alright? Gmm over capital R. Alright? So if you can see here, m and m cancel out, right? And you are left with VE square is equal to 2Gm by R. Okay, so from this you are getting the expression for escape velocity, which is under root 2Gm by R. This is the expression. All right. Now let us also find an expression for a very similar speed, which is orbital velocity, right? This also we are going to discuss for the very first time. All right. And for orbital velocity, as I have mentioned, we are finding the orbital velocity of a satellite which is revolving. All right. So it is revolving around the Earth. Okay, it is revolving continuously. So let's say, for example, it is revolving in an orbit. All right. So let's say this is the orbit which is outside the scope of this board. So I have just drawn a small path of this orbit. All right. So let's say here the orbital velocity is how much? V. Okay, and obviously the mass of the satellite is the same, small m. Okay, and remember mass of Earth is also the same, capital M comma capital R. All right. So now what are the forces that are going to act on this satellite? We are supposed to find the expression for orbital velocity. All right, and the symbol we denote is, let's say, VO. So we are supposed to find. So what are the forces? Right, the forces are namely gravitational force, and I will also tell you the value of that escape speed when it escapes. Okay, so gravitational force, that has to be equal to centripetal force, right? Gravitational force acting on the mass. So same formula, G m1 m2 by R square. G m mass of Earth, mass of satellite by R square. Which R we will use? Will we use this R? No, right? Because this is radius of Earth. So we need radius of this orbit. All right, radius of orbit meaning distance of this point from the satellite. This distance. All right, this is small r, let's say. So centripetal force will be small r square. Okay, and what will be the centripetal force? It will be mass of body into, isn't it, mv square by r. Okay, so now as you can see, you can find the expression for V as well from here, isn't it? Let's cancel the terms, m and m, r and r. So what remains is your orbital speed, right? So V square is nothing but Gm over small r, right? Gm over small r. All right, so this becomes your orbital speed. All right, so let's summarize, right? So orbital speed VO is equal to under root Gm over small r. Small r is your radius of orbit. All right, and let's say it is at a height h from the surface of Earth. So in that case, it will become under root Gm over r plus h, where this capital R is the radius of Earth and this is height from the surface of Earth. All right, G, as you know, it is the gravitational constant, and m, what is this m? Is it the mass of satellite? No, it is mass of Earth. all right, and escape speed, what was the expression we got? From the surface, all right, from surface of earth, this is VE. What was the expression? Under root 2gm by r, where r is what? Capital R, right? Because we are doing or finding the calculation from the surface. And this has a constant value. Why? Because g, m and r, they are constant, isn't it? Radius of earth, we already know, 6,400 kilometers. So substitute the value g, substitute the value. So in the end, you will be left with the magnitude of VE, which is 11.2 kilometer per second. All right, so per second. So I hope this one is visible. All right, this is S. If you want, I can write down below. 11.2 kilometer per second, which means this is a very high speed. All right, so this much speed that object needs to have to escape, isn't it? And that's understood as well, right? Why? Because the gravitational force exerted by the earth is very high on that small body, right? So that is why to escape, you have to have this much speed. All right. So let's see this question, right? What this question is talking about. Find the ratio of escape velocity for an object thrown from earth to orbital velocity of a satellite revolving near the earth, right? So you already know the expression, isn't it? Escape velocity thrown from earth. So what was the expression? Under root 2gm by r. And what was the expression for orbital velocity? VO, that is under root gm by small r. But small r becomes capital R here. Why? Because it is revolving near the surface of earth. So that small r will be capital R. Okay, I hope you have understood, right? This orbit is very close to the surface. So small r is capital R only. You have to take the ratio, right? So just take the ratio, under root gm by r, under root gm by r will cancel out. So what you are left with? VE by VO. That will be nothing but root 2:1. Okay. So first option. I hope everyone has got this one. Right, and this you can take as an homework, right? This you can take if you want as an homework. Let me just explain a few tidbits about this question, which is very similar, by the way, right? It's projected from Earth's surface with speed VE, which means it will have a kinetic energy. Kinetic energy will be half mv square, okay? Half m v square. And they have also said it is projected from the Earth's surface. That means it will have a potential energy also. What will that potential energy be? From the Earth's surface, meaning here also itself I am writing, it will be minus g capital M small m by r, isn't it? Capital R, right? From the surface. And then they are asking, find the total energy at a height, capital R. Why at a height? Because remember, with this speed, I just now said it will escape from the surface of Earth, right? So it is going to go up, isn't it? It is going to go up. At that height, what will be the total energy from surface of Earth? That's what they are asking. So total energy of the satellite you have to find out. So how will we do that? Simply, we have to do total energy will be potential energy plus kinetic energy. Okay, it's a very simple question. Just substitute the expression for VE over here and add them up. All right, and this will come out to be 0. So you can please check it out, this question. Okay. Just substitute the expressions, and let me give you a similar question also. Right, you can see this question, but here a small difference, which is here I am projecting again from Earth's surface, but not with VE. With what speed? 2 VE. Okay, but again from Earth's surface only. That means initial potential energy will be the same as the previous one. All right. So let's say initial potential energy here. This also I am giving as homework. It will be minus g mm by capital R. Right. What about initial kinetic energy? Again the same expression, isn't it? That is half m V square, but V is 2VE here. So 2VE square. Let me just write down the steps. So this becomes 4VE square, and VE, as you know, is under root 2gm by R, right? So it becomes 4 into half m. V square is 2gm by R, right? So 2gm by R. So you just have to cancel them, right? So 2 and 2 will get cancelled. So what does this become? 4 GMM over R. Okay. So initial kinetic energy we have found, initial potential energy we have found, which is literally the same question as the previous one. Here also I am asking the total energy at height R, because again with a higher speed we are projecting it, right? So it will go easily escape, and at that height what will be its total energy. So total energy, now what we will do, how will you find the total energy at that height, right? It would be nothing but the sum of initial energies, right? Because there is no dissipative force, right? If there is no dissipative force, the energy is not going to be lost, energy will be conserved. So now initially you have to find the total energy, which is initial kinetic energy plus initial potential energy, add them up, and that becomes the final total energy at whatever height. So that will be the total energy at height R or 2R or 3R or 4R. So just find this value. And this is pretty simple, right? And this is what I want you to do for that question. So this we have already done. So what will this become? 4 gm by R minus gmm by R. So this is nothing but 4 minus 1 gmm by R. So this becomes 3, right? 3 gmm by R. All right. And obviously, remember, as you can see, the magnitude is positive. Why? Because the magnitude positive, meaning it is going to escape the field of the earth. All right. And if it were to be negative, that gives you some indication that the body is somehow connected with the earth, either in the form of a satellite which is revolving around the earth. So the total energy is negative for that satellite, right? But if the total satellite gets a positive energy, positive total energy, the satellite will also escape the field of the earth. So please note this point, all right? Some students may get confused. All right, very well. Very well. We're going to another topic, right? Solids. This we have done so much, right? We have done about Hooke's law. We have discussed about the stress strain curve, right? And this is another stress which we had not talked about. So we are happy that we would be discussing it today, right? Breaking stress. What does this signify? It is the, we can say, the maximum stress that material can endure before breaking. Okay. Maximum stress that material can endure before breaking. Okay. So it is the maximum stress, right? The word itself signifies, right? The word breaking, it's somehow something is going to break, right? So this is the maximum stress. Some books, etc., it's also called it as fracture stress, right? Some can also call it as breaking strength also, all right? So also called breaking strength. So this also you can note down, right? And obviously, what will be the unit? It's a stress nonetheless, right? So unit will be same as the unit of stress, which is force upon area. So Newton per meter square. Okay. So the unit equal to Newton per meter square, or we just simply say Pascal, which is the unit of stress. And what does it depend on? Does it depend on the dimensions of the wire, right? So no. Okay. So it depends on, please remember, material of the wire. So these are some salient points you have to remember by heart. Depends on material of wire. Okay. So for example, let's say I have a wire hanging like this. All right. So let's say from here the wire is hanging, right? But what happens? Let's say because of its own weight, right? Because of its own weight, there is going to be a stress. And what happens when that stress is more than the breaking stress? So what will happen to that wire? That wire is going to break. Okay. So that means if the wire's weight or the stress caused due to its weight is less than the breaking stress, the wire is not going to break. But if it is more, then it will break. Okay, so let's see. So as you can see, let's see this question, right? A rope 2 centimeter in diameter breaks. They've already said it is breaks if the tension exceeds 600 Newton. So this is the force that is trying to break the wire, right? So due to this force, you get the breaking stress, right? And find the maximum tension that a similar rope of diameter 3 centimeter can withstand. Okay. So which means initially you can find the radius, and finally you have another wire whose radius also you can find. But remember, they have also said that a similar wire. So similar wire meaning they have the same material meaning they have the same breaking stress also. So the breaking stress is same for both wires. Okay. And let's say this one is the initial force F1, and here they're asking us the force F2 for the second wire, which will cause it to break. So the breaking stress is same. That's the property you are going to use over here. All right. So breaking stress, what is the formula for stress? Force upon area, right? So that means force upon area. Breaking stress of first wire is equal to breaking stress of second wire, right? F2 we have to find out. So I will just take directly from here F2 by F1, right? Bring F1 over here, A2 will go that side. So it is nothing but A2 by A1. And what is A, by the way? Pi r square, right? Because radius of the cross section is given. So area of cross section will be pi r square. So pi will get cancelled out. So it will be nothing but r square by r square, right? R square by r square. So I'm writing like this. Okay. And what is radius by radius? We can also express it as diameter by diameter, right? Because diameter is nothing but twice radius, right? So this can be expressed as diameter by diameter whole square. And this is given to you, isn't it? So F2 you can find out. D2 by D1 is how much? 3 by 2, right? So 3 by 2 whole square. 3 by 2 whole square will become 9 by 4 into F1. F1 is how much? 600, right? So just do the calculation. This becomes 150. 150 times 9, right? And that becomes 15 nines are 135, right? So the answer would be 1350 Newton. All right? All right, very well. So that question was done. Let's see this question. It's also pretty basic. If you see, it's a very good question. Breaking stress depends on. So remember, it won't depend on the length. It won't depend on the radius. It is exclusively dependent on material. Okay, so it's a very straightforward question. Now let's do another. So here also, if you see, the length and radius we are changing, right? So the length of the wire is made 3 times longer, and the radius is halved. So half the radius. So the dimensions of the wire you are changing. But now what are they asking over here? To its respective values, then the Young's modulus of the material of the wire. All right. Young's modulus also, you know, just like breaking stress, it depends on the material. So it depends on the material. It is irrelevant no matter what or how much you are changing the dimensions. It is irrelevant as far as Young's modulus is concerned. Okay. So it means it will remain the same. Young's modulus will remain the same. It will depend on the breaking stress. All right. Let's do another. Yeah, I think Tanmay is asking, sir, kg weight is unit of. It is obviously, it would be a unit of force, right? If you see in the wording itself, it is the hint is being given. All right. All right, very well. So let's see this question. What will be the answer? Young's modulus, obviously it won't be dimensionless, and Young's modulus, just like breaking stress, has the same unit as stress, which is Pascal. All right. So which means the correct answer will be, has dimensions same as pressure, okay, which is Pascal. So that's why that one. All right. So this one is Pascal, or we can say Newton per meter square. All right. So these are wrong, right? not force, not power, but Pascal. All right. Very well. Very well. Let's move on to another. Right. So here, if you see, a force has been given. It has been shown to be applied on this cross section of this wire. All right. Of uniform cross section. That's also given, as shown in figure. Then length of wire is increased by 1 millimeter. The length has been increased. Okay. So remember, length has been increased, meaning delta L, the change in length, and this is your force F, and they are asking the energy stored in the wire. Right. This we have done in our previous discussion, if you remember, half into stress into strain. Right. What was this? Energy density in that wire. Right. That was coming as joule per meter cube. But here they are asking not energy density, but energy stored in the wire. Okay. So if you see over here, right, if you see over here, so let's say this cross section is A. All right. Let's say initial length is L. Initial length is L for that wire. So what will be energy density? Half into stress into strain. But what will be energy stored? You can directly use the formula if you know. Otherwise, we can derive it as well, right? Half into stress into strain. Half into stress. Stress is what? Force upon area. Right? So force per unit area into strain. Strain is what? Change in dimension by original dimension. So delta L by L. L I have mentioned. Delta L is mentioned over there. Right? Delta L by L. And this, remember, I just now told you, this is energy density, not energy. Which means after finding energy density, you have to multiply it by volume of the wire. So just now I mentioned this is area A, length L. So total volume of the wire will be how much? A into L. Okay. A into L. That means you see L and L cancel. A and A also cancel out, right? So what are you left with then? You are left with, right? You are left with half into F into delta L. That is all you have to do in this question. Okay. Half into F into delta L. And both of them were mentioned in the question, isn't it? F is also known, delta L is also known. So let's find out the energy stored. Half into F is 100. Delta L is 1 millimeter. 1 millimeter in meter or in SI unit can be written as 10 power minus 3 meter. So you have to write in SI unit. Okay. So now if you can see, this is 1 by 1000, isn't it? So this is 1 by 2 into 100 by 1000. Zeros cancel out. So it becomes 1 by 20. Right? And 1 by 2, as you know, is 0.5. This is 0.5 upon 10. That means 0.05. And what is the SI unit of energy? Joule. And remember the SI unit of energy density as well, joule per meter cube. Okay, anyway, so we got the answer, 0.05 joule. Okay. So please remember those formulae. All right, and this also, we have done the classic formula in the case of nuclei. Right, now we are jumping into your 12th class, isn't it? If you see here, regarding nuclear radius, they have mentioned, right? Nuclear radius of this nucleus is given. Fermi meaning FM. Okay. And remember the formula for nuclear radius. What was it? R is equal to R naught A to the power 1 by 3, where R naught is a constant, 1.2 femtometer or Fermi, 1.2 FM, and A is your mass number, right? And if you see over here, mass number is also given, isn't it? What is the mass number for this one? 64. What is the mass number for this one? 125, right? So if mass number is known, you can find the radius as well. How? We'll just take the ratio, right? So for example, so let's say I'm writing it as Ry over Rx. Okay. So radius is R naught, right? So it will become R naught Ay to the power 1 by 3 whole divided by R naught Ax whole to the power 1 by 3. Okay. So R naught also cancel. It will become Ay by Ax. Alright. So it is simply AY by AX whole to the power 1 by 3. AY is how much? 125 by 64. 124 cube root is how much? 5. 64 cube root is 4. So this you can directly write down as 5 by 4. Okay. Rx is given to you. Ry we have to find out. So Ry will be nothing but 5 by 4 into Rx. Right? Rx. So what will this become? 5 by 4 into 4.8. For me, 4.8 and 4, 1.2. 1.2 times 5 is 6. So 6 for me. Alright. So 6 for me, that means you get your answer. Alright. So this is the expression. Please remember this classic formula. Right. And remember, we had also discussed regarding density also. Right. What did we say or discuss about density? Density will remain constant, irrespective of what the mass number is. And as you can see, this next question. Right. So density of the same nucleus has been given as rho, and now density of the other nucleus I am asking you. That is 125 nucleus, and that I am asking you. So what will it become? Will that also change? Because remember, the radius has changed, right? From 4.8 to 6. Why? Because mass number has increased. So mass number increases, radius also increases. But what about density? Density will remain constant. Okay? This we had discussed earlier also. If you want, we can prove this also. How will we prove it? Density is total mass upon total volume, isn't it? So let's prove it if you want. So mass upon volume. Okay, let me write down like this. Mass number is known to you, right? So mass number is, let's say, A for now, A. And what will be mass then? Mass will be nothing but mass number. Mass number implies how many nucleons are there. So mass number into mass of one nucleon, or let's say mass of one proton or mass of one neutron, whose both mass we are taking it as to be almost same. Okay, so 1.67. All right, so it will be mass of proton. Okay, so 1.67 into 10 raised to the power minus 27 kg. Okay, kg. This is the mass. And volume. Volume we already know, it is 4 by 3 pi r cube. Right? R cube. What will r cube become? R cube is r naught cube into A. Right? R naught cube into A. So now if you can see over here, A and A cancel out, right? And what remains is a constant value, right? A constant value which is this numerator 27 kg upon 4 by 3 pi r naught cube. R naught, as you know, is 1.2 Fermi, right? So it means 1.2 into Fermi. Fermi is how much? 10 raised to the power minus 15 meter. Okay, so whole cube. And if you solve it, the answer will come in kg per meter cube. Some constant value will come. That value is not important, but this concept is important, that rho remains same. All right, very well. So let's see the next question. So I hope you found that question interesting, right? And atoms as well. We had done lots of questions on atoms regarding, if you remember, we had done for the maximum wavelength and the minimum wavelength during the transition of electrons in one particular series, right? If you remember, we had talked about this table, right? So for one series or one jump that electron is making from, let's say, outer orbit to lower orbit, what is the maximum wavelength associated with the photon, or minimum wavelength associated with the photon? All right, so we had done this. Now let's see this question, what this one talks about. Here they are saying frequency of the series limit of Lyman series is nu 1. And again another they have written, if you see, frequency of the series limit for Balmer series is nu 2. What is series limit, by the way? And before we go to that, let's read the next line. The frequency of the first line of Lyman series is nu 3. So what is first line of Lyman series? 2 to 1, isn't it? 2 to 1, if you remember this diagram. Lyman series, right? These lines. The first line is 2 to 1. And what is the series limit? Series limit meaning from infinity to 1. okay, for Lehman series. So please remember, for series limit is nu1. If you want, we can draw it in a separate diagram, right? So let's say this one is n equal to infinity, this is n equal to 1, and let's say this is n equal to 2, right? Series limit for Lehman series given as nu1, right? Which means for this jump from infinity to 1, the frequency associated is nu1. And for Balmer series, series limit is nu2, right? You can see frequency for series limit is nu2. So we can draw from infinity to n equal to 2, right? This jump frequency associated is nu2. And what about the remaining one? It is first line of Lehman series, which is this one, n equal to 2 to 1. Okay, so let me draw over here. So this is nu3. All right, if you can see, right, this is what we have drawn it on a separate diagram, that's all. Now you can mention them in the form of energies, isn't it? How? You see this energy, this whole energy transition, whatever energy is associated with this transition, that energy can be equal to, or we can write that as equal to, this energy is equal to this energy plus this energy. Okay, so that means this top energy, this whole energy, that is h nu1, or let me just write it as E1. So energy from here to here is equal to energy of this one plus energy of that one. All right. So energy of 2 plus energy associated with 3, right? Because remember, when that electron is jumping from outer orbit to inner orbit, it is going to emit an photon. That photon will have energy E. So that energy we are talking about, right? And that energy can be written as h into frequency of that photon. So that means h into, right, h into frequency of that photon. Similarly, this one, h into frequency of this photon, h cancel out, and what you are left with is nu1 is equal to, right? So if you can see the option, this one, right? Nu1 is equal to nu2 plus nu3. H cancel out. Very well, right? So I hope that was an interesting question. Remember, we can ask similar questions. So let's say, for example, first line of Balmer series is given as nu1, then first line of Paschen series is given as nu2, right? And then let's say series limit of the series is given as nu3 or nu4, whatever. But for that, make sure that you can draw such simple diagrams, you'll be able to get the answer. All right? Okay, very well. Now see this question, it's a very oral question, right? In hydrogen atom, energy of first excited state is this much. Find the potential energy of the same orbit they are asking. Here there is no need to do any calculation, right? Potential energy of electron in that same orbit, okay, in that same orbit, it is written like this. Potential energy with nothing but double of the total energy, right? Total energy is given as this one. The answer would be double. So double meaning, just double it, minus 6.8, that's all. And remember, first excited state meaning n is equal to 2, right? The second orbit, all right? Let's do a very simple oral question again. The same question, but here I'm asking the kinetic energy in that same orbit. So kinetic energy would be nothing but just reverse the sign for total energy, right? So here minus 3.4, the kinetic energy would be simply plus 3.4. Okay? Very well. Very well. So I hope you guys are not bored. All right. And remember, we had talked a little bit about centripetal force as well, right? Just a few moments ago, if you remember. So right now, the last topic of the day is going to be laws of motion, right? And centripetal force, remember, is towards the center of the circle, right? Remember that particle is rotating in a circle, or previously, if you remember, I had drawn a satellite which is revolving in an orbit. So centripetal force is directed towards the center of that orbit. And who was providing that centripetal force? The gravitational force here, okay? So this is a general diagram, all right? So let's say this is the particle which is revolving in that orbit, and it is revolving with speed v, which is called the tangential velocity. And for that velocity, you will get a centripetal force, right? Because then centripetal force has to be directed towards the center, right? So let's do a small discussion about the centripetal force as well, right? Which we did not have in our discussion on gravitation, right? So centripetal force is or can be expressed as mv square by r. R is smaller or capital R? Please see the diagram. It has been written capital R or small r. So here radius is smaller, right? And for that centripetal force, you will get a centripetal acceleration. Why so? Why so? Because remember, net force is mass into acceleration, right? So this force can be written as mass into acceleration. So mass into acceleration. C for centripetal. Now if you see, mm cancel out, right? Mm cancel out. So from here, you are getting the centripetal acceleration as well, all right? Centripetal acceleration, that is AC. That is nothing but directly v square by r. Okay, and remember, here this acceleration is also directed towards the center of the earth. So that is why they have called it radial acceleration. Okay, so please note this term, all right? Radial acceleration, why? Direction is towards the center. Centripetal force is also directed towards the center, all right? And remember, the body is rotating like this, so that is why angular velocity has been drawn, all right? So it is rotating in anti-clockwise manner, right? Now, what is this force, right? I think the remaining terms we have already covered and explained. Now, what is this term? Centrifugal force. This also we will be discussing for the first time. So remember, so let's say for example you have a turntable, all right, a turntable, or let's say a disc which is rotating. Okay, it is rotating with this constant angular velocity omega, right? And let's say on that turntable you have kept a small block at the edge of that turntable, right? That means as the turntable rotates, it's going to have a velocity tangential, right? Tangential. Now what about the acceleration of that block with respect to the turntable? Because just now I told the turntable is rotating, right? But with respect to the turntable, what will be the acceleration of block? It will be towards the center or away from center? It has to be away from center, isn't it? Remember, the original acceleration is towards the center, but with respect to this turntable, the acceleration of block is going to be away. So if this is centripetal force, so with respect to the center, which force is going to be applied? Centrifugal force. Okay, this is very similar to the pseudo force topic which you cover in this laws of motion chapter, all right? So this centrifugal force also has the exact same value, okay, that is mv square by r, but just remember the direction is going to be different, all right? And we can also express both of them in terms of omega also, right? Because v is r omega, so this becomes m r omega square. So both expressions are valid, all right? But the directions are reverse, all right? Very well. So let's do this question. If you see over here, what is given, right? The radii of circular path of two particles of same mass. So mass has been specified to be same. Are in the ratio 4:9. So the radius ratio is given. Okay. So R1 by R2 is given as 4/9. All right. Then let's see what will be the ratio of their speeds if they are acted upon by equal centripetal force. So that means speed ratio they are asking. But centripetal force is same. All right. Centripetal force is same. So what is the formula for centripetal force? Just now we discussed, right? It is m v square by r. So can you find the expression for v from here? So what will be v? V square can be written as, take this r over there, so fr upon m. Okay, and now if you see over here, f is constant for both the blocks, f is same. Mass is also same for both the blocks, mass is also been given to be the same, right? So now what can we write? Can we write, take the ratio, directly take the ratio, right? So that means I'm directly writing v1 by v2 whole square will be equal to what exactly? You can take hint from here, that is v square is proportional to r, because they are constant. So V1 by V2 will become R1 by R2, and R1 by R2 you already know, 4 by 9. 4 by 9, that means 2 by 3 whole square, right? And from here you're getting the final answer. V1 by V2 becomes equal to 2 by 3. All right? So please remember, whenever such questions come, please draw a circle, right? You can draw the direction of forces also, right? But there need not be the case that whatever object is revolving in a circle, it will have only centripetal force, right? There could be other forces as well. So for example, let's say this is the object, right, which is revolving in a circle. Okay, this is the object revolving in a circle. So obviously now we discussed about centripetal force, but also remember there could be another force which can act tangential to the path of the circle, right? This force provides or makes sure the body revolves in a circle. So its magnitude is mv square by r. But what about this force? What is its purpose? Its purpose is to change the speed of the object. Okay. So that means in our question, what we discussed over here, so there is no tangential force, right? So that means the speed is going to remain the same because no one is there to increase or decrease the speed. So this is what we call uniform circular motion. All right. But if you see in this diagram, this won't be called uniform circular, right? Because the speed is changing. Okay. So here we can call or say it non-uniform speed. The speed is changing. So this is not uniform circular motion. So please remember, all right? So this is not uniform circular motion, UCM. Okay. So I guess that's it for today. I hope you guys had a great time. Please keep revising, keep practicing, and we will be back with another such session. Thank you.